Hello, everybody. Let us start our discussion today. Today, we shall be trying to see some of the uses of the language of differential geometry, what we are learning so far. So, some of the uses of vectors, one forms, and also the metric. So, again, let us start by recapitulating what we have learned so far. So, we have first started with vectors, and we have to go in this journey quite along from where we are now. But let us build up things slowly, and in between, like in today's discussion, we'll try to understand them in some physical contexts. So, vector we wrote this way, and we said that we can write it just like the old vectors we learned in our schools in terms of its components. And the basis coordinates we have chosen. The basis also chooses the coordinate. And we let me keep it with blue here. So these are contravariant components. Sometimes in the old language, these are called the contravariant components. We are essentially calling these as the components of the vector. Then we learned about the one forms. One forms has tensors. So they are tensor of this type of rank 1. And there is one place, one slot downstairs. What are these upstairs and downstairs? We have not talked about yet. We will definitely talk about them. And this we represented this way, which we said is a device. It is a device so if I have a one form, and at the end of the last lecture we said that we found that for every vector A there is a corresponding one form. This is true if the metric exists in that particular space, but we have not made that comment yet, but let's keep it here. Let's keep it for future. The one forms can also be written in terms of some components of the one form and the basis one form. So this is again a one form. But this is the basis one form, and these are the components. How do I get the components from the one form? Remember that if I just put the basis which I have here in the one form, the basis vectors in the one form, that gives me the components. Okay. And we got this relation. Essentially, this is telling you if I take the alpha-th one form basis, and in that I can put in a vector. So I put the beta unit vector, beta-th unit vector. This is 1 if alpha equals to beta, it is 0 otherwise. So this is a 4 cross 4 objects because we are dealing in 4 dimension. It is diagonally 1, otherwise it is 0. This is something that we'll come back to later, but that is what we have got. So as we have just stated, for every vector A, I just put a star here to remind you that we will come back to this statement later. We will find that there are cases where there is not, you will not find a corresponding one form for a given vector. But for the case we are dealing with here, for every vector A, there is a corresponding one form. Well, these are just notations. Now, what is so special about these two? Well, they, as you can see, they come in pair. So if you give one to the other, this essentially means if I write A tilde in terms of its components, so this is like A alpha, the one from alpha. And the one from alpha will take the vector A, and the vector A, say it has components A, beta, and the unit vector beta. So I can write vector A like this. So which essentially gives you A alpha, A beta, and then the amalgamation of the two bases. So you realize that A tilde A is essentially A alpha, A alpha. Remember, because this quantity W alpha taking an E beta we have written here is delta alpha beta. So if I work this out, this is A alpha, A beta, and then I have a delta alpha beta. If I do the sum over beta, for example, then when beta is not equals to alpha, this quantity is 0. So only those terms will survive where beta equals to alpha. And that comes only once. And there I can just write alpha for this beta. So that gives me A alpha, A alpha. So that is just a short workout. I will not keep this here. But I will remind you that the same result I could have gotten if I would have written A alpha, A beta, G alpha beta is the same scalar. So by doing this, we are getting nothing but A dot A, and it also gives us a nice property of the metric, which will come to. Essentially, we can identify what a metric does to a vector. Before we come to that, so let us look at the transformation properties of this, and there we will see some combinatorics. This we have gone through many times, but let us still write them down. So I have, if I want to go to the primed frame, say I write A alpha prime, that I can write as lambda alpha prime beta and then A beta. So A alpha prime is a component of a vector, and the unit vector in that case will transfer the exact opposite way. So I will have beta here and alpha prime here for E beta. If you look at the components of the one forms, or let me remind you, these components, just like contravariants, these components are also called covector or covariant components. Okay, so what was the transformation rule for the components of the one form, it transforms just like the basis vector transforms. So I'll get this again here, and sorry, A beta, and the basis one forms will transfer like the components of a vector. So there we saw the dual nature last time. Okay, so what you should note here is that if you look at the left hand side and the right hand side of the equals to sign, if in the left hand side of the equals to sign I have an index alpha prime upstairs, then in the right hand side also that index is upstairs. Okay, in the number of indices upstairs in the left hand side is the same index actually upstairs in the right hand side. The right hand side I have always a summation over beta, the way we have written this down. The right hand side always have a summation over beta, and remember the beta summation can only be done, or any summation can only be done using the summation convention when you get one downstairs index with the one upstairs index, right? And that is maintained everywhere in the right hand side. And once the summation is done, that index which is summed over is not important. That index is already worked upon, so that is not important. So that index has actually disappeared from the from the combinatorics of keeping where the indices are. So that beta index is never counted. The right hand side also have the index alpha prime, sometimes upstairs, sometimes downstairs. Okay, so with this, let's see that what are the things that we have noticed so far. We noticed that one forms are rules. This is important again, that one forms are not vectors, they're rules. And so as the metric that we are talking about, and the one forms that we have talked about, those takes a vector in input and gives out a scalar. Right? So that is what is called as one form. Once we have chosen a reference frame though, that also means that the associated basis vectors are specified. I mean basis vectors here, not basis one forms. So let me emphasize that with this. So these are known once you have chosen the reference system. We can define components of one form by using basis vectors as input. Okay, so this we have seen already. I am just writing it down again to remind you again. So if I put the alpha basis vector as input, I get a component, alpha component of the one form. Now, we also saw here that these have certain transformation properties. So, components of the vectors and the one forms transform in certain way. Now, sometimes these transformation properties are used to define these vectors or one forms. So, sometimes these transformation properties are used to define the vectors or one forms. So, a few things to notice here, that if I choose a vector, there is a corresponding one form, at least in the kind of system that we are working on, there is always a corresponding one form. The vector, when I choose the components of the vector now, I have to choose the basis vectors. The basis vectors, the one form, the basis of the one form, and the vectors, they have certain transformation rules. Once I have chosen the bases, then the components are fixed. Now, one way of telling you the algebra and the analysis of these objects is to tell what is the algebra and analysis of these components. And that is quite well used in this type of calculations, and we will also probably use it sometime in future. And one more comment here. Scalars. Sometimes these are written as tensor of rank 0, so it's written like this. They remain invariant. Under the transformation, under the coordinate transformation. Remember that the coordinate transformations, we said that there can be 10 coordinate transformation, 4 translations, 3 space-space rotations, and 3 space-time rotational Lorentz transformation or boost. Now, for all of these, I can define, for each transformation, I can define a scalar. And for example, right now I am talking about scalars which are invariant under all rotations. Okay, these are the thing we observed, and we also saw a very important type of tensor, which we call the metric tensor. We will see that this will be the thing, the object in when we'll study general relativity. This has a tensor of form this. So as a tensor, it takes two vectors, gives a scalar, which is essentially the dot product between these two vectors by definition. If both vectors are same, the metric gives the norm or the length of the vector. And that's why it's called a metric essentially. This also has another property which we saw last time. It converts a vector into a one form. And this we saw last time, that say I have this metric which we write with G. It has, I give the vector B, this already, and the unit direction beta, this will give me B alpha G alpha beta. Which we saw is same as B beta. I'm sorry, beta downstairs. So why did we say that it converts a vector to a one form? Because if I keep just one of the slot fixed, which is that vector slot, the first vector, the vector I want to transfer to a one form, if I put in there and keep the other slot empty, then you see this is a one form now, because it will take one argument which is a vector and will give you a scalar. That's what one form does. If you look at the thing component wise, here I get the component of a one form by multiplying the components of the metric with the component of a vector. And that is interesting. This here also I see the component of the vector gets transformed to the corresponding component of the one form. Both I have written B because they are related, they are not arbitrarily chosen. Now here you also see that in all these cases where I am using index upstairs and a downstairs, that index is summed over, that is disappearing for my total count. That is called a contraction. So I'll just keep the name here. And in terms of the index, which is sometimes is very useful because that's, let us keep our calculations correct. In terms of the index, this is a lowering operation. So I had the index upstairs as B alpha, and then that index using the metric I have bring it downstairs. So that's why sometimes it is also called a lowering operation. Okay, so these are the properties of the metric, and the norm, just let me remind you that G alpha beta, B alpha, B beta is the norm. And if you remember, I could have also gotten it this way. and I can write these two together as b beta. So I can write the same thing like this also. So this is interesting of interesting of writing the same thing in many different ways. Okay, before we go any further, let us start with a physical example now. So let's call it a wave. Let's think about a wave. A wave, so let's call it psi as a function of the vector x. In our old notation, so we should match with what we already know and what we have learned. So I used to write this as, let's say the amplitude is 1, there is nothing that is of importance. This k and x are 3 vectors, so I can just write it like this. So let's see how can I write the same thing in our new notation. Okay. So because I have already written a vector there with the arrow, so which is a 3 vector. So let me emphasize that we are talking about 4 vectors and 1 forms. Okay. So what is the vector for? And now I mean a 4 vector. The vector corresponding to x is this, which is, I can also write that as x alpha e alpha. The question is, what are its components? Well, remember, x alpha components are ct, x, y, and z. Similarly, another vector which we call the vector k, as always, k alpha. I'm obviously writing all the vectors in the same basis. And if I ask what are the components in that basis, this in index notation, it's by definition, these are k0, k1, k2, k3. But what are these? This is k0 is omega by c, k1 is kx, and this x suffix doesn't mean that it's a component of a one form. This just is the component of the 3 vector. So let me emphasize that these are components of the vector k. This is a 3 vector k. Okay. Now if I have this, then this entire quantity, if I call it say phi, which is the phase, then phi, which you remember is a function of all of these x's. So phi is different. Phi for the wave, the phi is different at different events, space-time positions. I have all x alpha here. Phi is different for different events, but it's a scalar because I can now write this phi as g alpha beta x alpha x beta. Sorry, k beta. Or if you wish, I can also write this as x alpha and then k alpha, where you know now k alpha is the components of a one form. And what will be k alpha? Now I know how to get k alpha out of my components of the vector as written here, because this will be g alpha beta and then k beta. So let's see what are these components. So when I write with the second bracket, it means I want to write down all the components. So let's say, what if alpha equals to 0? If alpha equals to 0, I have four options. I have a sum over G00, G01, G02 and G03. Every time I have K0, K1, K2 and K3. But the only thing that will survive is G00, which is 1, because all the other are 0. And if G00 is 1, then this is just K0, and K0 is omega by C. What about K suffix 1? Well, K suffix 1 in the same token will be G11, K1. And G11 is minus 1, so this will be minus Kx now. And you know what the others are, minus Ky, minus Kz. So you see that I get phi equals, and I should have an I here, I. How do I do the sum? X alpha, K alpha. Well, first 0, x0, k0. x0 is Ct, k0 is omega by C. So the first term is Ct itself. I'm sorry. Ct times omega by C is omega t. The second term is x1 is x and k suffix alpha is minus kx. So this is x kx minus y ky minus z kz, which is what I wanted to have. So if you really wish, I can write down this as omega t minus k dot z, k dot x. Right. So you see, there is an advantage of using this notation. The advantage is the following. Just looking at this phi, nobody will be able to tell, just looking at it, that phi is a scalar. But if I write phi this way, so phi we have written as I x alpha k alpha, we know that it is a scalar. So this is also, if you wish, this is the k1 form taking the x vector in. It should give me a scalar. So they're all equivalent, but these two tells me by definition that this is a scalar. All right. And also remember that phi can change between any two events. Now let us use this phi. Let's see what happens. So let's think of one situation, a thought experiment, if you wish. It's not an experiment actually. It's something happening. So let's call this an example rather. So what is the example? The example is that I have this phi defined everywhere in space, which is a scalar, and phi is a function of all these coordinates. So when I write with a set symbol, it means that it's function of all four values of x alpha. Now, which means that if I draw a space-time diagram where my x-axis represents, so this is again it's a representation, this is not a real diagram, real plot. So this is my space-time diagram. So everywhere, one point in this diagram is an event. Everywhere, phi value is different. For every event, phi value is different. So for every event, phi is different. But what do we mean when we call it a scalar? We mean that if we talk about the same event and measure the value of phi from different reference frame for that given event, that phi value as measured for different reference frame of the same event will never change. Okay, that's what I mean when I say phi is a scalar. Now imagine that there is an observer moving with a trajectory, some arbitrary trajectory. So this is the world line of an observer. Remember, world line of any observer I can level by tau. So this is say tau 1, this is say tau 2, and any point here I can level the world line by tau. Tau is the time spent in the clock of the observer himself. And if I take any point in the trajectory, I can also define a tangent to that point in the trajectory. Maybe this, what I have drawn, doesn't look like a tangent, but just imagine this is a tangent. And this angle is theta. And remember from your classes in special relativity, tan of theta is c by the velocity of that observer. And this is the 3 velocity I'm talking about. Okay, so it looks very odd if I put the vector sign over there. So just imagine that the horizontal axis here is one spatial coordinate x, and that v I have written is vx. So that is the velocity I'm talking about of the observer at that point. And the velocity I can also level by tau if I wish, because the velocity can change at different points. That actually defines the trajectory. Okay. So the question we ask is, remember that phi was defined everywhere in this region. So how phi changes along a trajectory? I could have written word line also along the trajectory of an observer. It's same as the word line. Okay. So this is the question that we are asking. Okay. Now, when I say change, I start with infinitesimal change. So infinitesimal change in phi is d phi by definition. And if you want to really write it down, so d phi is function of x0, x1, x2, x3. Let me write those explicitly. And this x0, x1, x2, x3 are the points measured here along the trajectory. So they can all be labeled by the proper time tau. So this is function of tau, x1 is a function of tau, x2 is a function of tau. So though phi is not an explicit function of tau, but through the dependence of tau in x0, x1, x2 and x3, it will be a function of tau. Remember that this we are saying for a very specific case. We are not saying how phi changes, we are saying how phi changes along the trajectory of an observer. That is important. Now, once I have things like this, we know that simple analysis tells us that I can calculate this by its change along every x and then supplemented the change of x along every tau. There is a sum over alpha, and this is nothing but this is coming directly from the chain rule of partial differentiation. There is nothing that we have learned in this course which is required to write this down apart from the summation convention. Let's stare at it a little moment. What is this? Well, these are by definition the components of the four velocity. Right? Which is multiplied by something, and after that multiplication, what I get is a scalar. So what should I write here? Should be component of on one form. So remember, one form I write usually with this tilde sign, and this one form is about d phi, so I write this sign for this one form, and what is sitting here is the alphath component of this. In fact, you can verify this just writing it down. I write with del phi del x alpha. Let's see that I can write it this way. I put this component of one form by force, and inside it I need a vector which is the velocity 4 vector. If I forcefully write this way, so does it give me back what I have earlier? So let me keep this a little bit downstairs and I will work our way back. So let's keep it somewhere here. So let's see what is the previous line. So del phi del x alpha remains as it is. U, I write in terms of its components and the remember that I have done a mistake here. You can see I should use a separate index, otherwise that summation will be problematic. So this is the corresponding unit vector E beta. So that is equals to del phi del x alpha U beta, and then when I do W alpha on E beta, what I get is delta alpha beta. And you can see in a master stroke from the third line, you can go to the first line by using the property of delta alpha beta. So indeed, these are components of a one form. What are these called? We know that these are called gradients. So here we have learned that the gradients, remember we used to call it a vector, but it's really not a vector. It's a component of a one form, or the gradient is a one forms, or you can call it a covector in the old language. How will these components transfer? So let's also look at the transformation rule once. Transformation rules. Does they transfer the right way as a one form transfer? Well, let's see. So if I have del phi, okay, so let's first say what is a transformation, and now first we will use our knowledge on coordinate transformation, which has nothing to do with again what we have learned in this course apart from the summation convention, which is convenience. So let's say that I have x prime alpha, which is the transferred coordinates, and this the transformation is that it will be related to the original coordinates, right? So which means if I want to calculate del phi del x alpha prime, then by chain rule I can write this as del phi del x beta and then del x beta del x alpha prime, just by using chain rule. These are components of one form, these are components of one form. How are they supposed to transfer? That we have worked out earlier. They're supposed to transfer the following way. With a lambda, beta here, alpha prime here. So what is it telling you? It's identifying these two. It's telling you del x beta del x alpha prime is lambda beta alpha prime. The left hand side here is more general. Lambda is the Lorentz transformation matrix, but we will see that when we will go to more complicated cases, then we'll revert to the more general form del x beta del x alpha prime. Okay, so this is what you have learned here, is what you have seen here is first we have looked at a wave and have seen how in a coordinate independent form the phase of the wave, which is a scalar, can be written. So this is the coordinate independent form. You can also write in this way where it requires the components in that coordinate of the one form and the vectors. But it's also manifestly Lorentz invariant or manifestly transformation invariant or manifestly scalar. Why do I say that? Because I have one index upstairs, one index downstairs. By now we already know that such object does not have any hanging indices around, so that's a scalar. Then we ask the question that how does such a scalar changes along a line? So the change of scalar along a line is also obviously it's also a scalar, and I wanted to find this. The reason is in the next line where I have used the time derivative in the right hand side but forgot to write in the left hand side. But how phi changes as a function of tau, this left hand side is a scalar divided by a scalar. So this is also a scalar. And from that we argued that these quantities are components of one form. And we wrote down the d phi d tau in the language of one forms, and we came to the conclusion that gradients are components of one forms, or in the old style covectors. Then you look at these transformation rules of the gradient, and that told us that del x beta del x alpha prime is essentially the lambda alpha beta. Okay, this is what we have done so far. Let's also look at the derivatives. How do we represent the derivatives, which is related to what we are doing now. And this is mostly just a representation because you will see later it will come very useful. So if I have to take the derivative of del phi del x alpha, which is what we have been writing so far, this will use the shorthand. This is a shorthand, or if you wish, it's a notation, nothing else. It's not that we are proving anything here. So this is phi and then comma alpha. That comma alpha means I have taken a derivative with respect to x alpha. Okay, so this is let's take some example. So if I have say del a alpha del x beta, this in this funny notation we'll write del comma beta a alpha. Say del a alpha del x beta Okay, so things like this. What about if I have del x alpha, which is a vector, which is just like this case, del x beta? Well, this, as you'll see, this is something that we'll write as del comma beta x alpha. But this is 1 only if alpha equals to beta. So this is essentially alpha beta. But delta alpha beta is also, remember, it's delta alpha beta. This quantity is not then a tensor of rank 2. It's rather is a one form. Because remember, this is omega alpha e beta. This is what we have seen earlier, which means this I can call as the one form dx alpha. Okay, one form this is the one form in the exact same sense as the gradient is a one form. Remember, for the gradient one form, this was given by this. So only thing that has happened for this particular one form is that I have replaced phi by the alpha component of the x. So I can write the alpha component of x is used instead of phi. So just like d tilde phi was a one form, this is also a one form. And what is this one form? This one form is a special one form. This is essentially the one form W alpha. So this is the basis one form. So the basis one form, sometimes I can also write as d tilde x alpha. Oh, just use it in the d phi ones. So d phi is the one form d phi operating on the vector x. The one form d phi I can write as del phi del x alpha and omega tilde alpha, which I can now write this way, which is taking the vector x. What is the vector x? It is dx alpha, or not careful, beta, this, and you see that we get back this calculation. Actually we have done once, but in a little different looking fashion. So I get this. Which is essentially delta alpha beta. So you get d phi equals, right? So this is delta alpha beta, and once you multiply that with, do the beta sum, that's dx beta becomes dx alpha. Okay, so this is a very interesting way of writing the derivative, and very short and very useful. We'll see that we will have to modify it a little bit for the derivatives, as the derivatives get modified when we'll do general coordinate transformation. And I'm sorry, when we'll do general relativity. And as you see that how the derivative of x alpha with respect to x beta is essentially the basis one form. Let us look at some geometric understanding of the vectors and the one forms. So when I say vectors, the geometric understanding is something of a headed arrow, which we already know of, but we will still look at it. So the vector is the vector A, and let us say that we will deal with a two-dimensional vector such that I can easily plot this in this board. So the vector is vector A, and it's a directed line segment, so it looks like this. Okay, so this, remember, I can write as in terms of its components. So in this case A1, the basis vector E1, plus A2, the basis vector E2. So the basis vectors are, say, the basis vectors, one vector is this way. So this is E1, and the other vector is this way. This is E2. So these are the two basis vectors. Okay. So how do I get the components along these two basis vectors? Well, I use the rectangular rule for the vectors. So I get the component along 2 like this. I'm not going through this with a lot of explanation because I guess this you have done fairly well, even in your plus 2. So this is A1. So this is what I mean. This is the picture of a vector that is there in my mind. That is to say, the components are how much is the projection of that vector along A2, how much is the projection of that vector along A1. What are one forms? So say I am talking about the one form B. Okay, remember it's a rule. Now the one forms, in case of some n-dimensional case, are a family of surfaces. But because we are dealing with 2D, we'll just consider them as lines. Because it's 2 dimension, the surfaces will be more like a line. And these are the family of lines, so parallel lines. It's like this. What is the operation? If I put my vector in it, the operation BA results in a number which is how many surfaces the vector has gone through. Okay. How do I get the component of B? Well, instead of any vector A, I put those unit vectors. And you can see this is E2 and this is E1, just as before. You can see in this particular example, what do you think is B1? Well, B1 is the, how do I get that? It's B tilde E1. The E1 is the vector which I have put in, and I have to calculate how many surfaces the vector has gone through. The answer is 1. In this case, B1 is 1. What about B2? Well, B2 is parallel to the surfaces, so B2 is essentially 0. So what is the one form? This one form is nothing but the one form which has 1 0 component, and that component, that one form, is the unit one form. Okay, so this is one way of looking at the geometry of the vectors and the one form. Although in this example, B came out to be the basis one form, that is obviously not necessary. That is how it's chosen the example. B can be anything. I'll stop here today. We have gone through some physical description of the things that we have learned so far. We'll go ahead with our learning further in the next discussion. Thank you.